Thank you for the kind words, and thank you also to the organizers for inviting me and letting me speak to you this way. It's a shame that I couldn't make it to Montreal this week or this set of weeks, but hopefully this will be a good alternative, a good compromise that I can still give my lectures, which I'm very pleased I'm able to give. Yeah, it's a series of three mini lectures, and so the title is The Origin of Trigonometric K-matrices, and I will address that really in the last lecture, which is more like a research talk, and I want to kind of gradually build up to that. So in this first lecture, I want to give some background over the information, some overview. And so here is a rough schedule for my three lectures. So today, as I said, I want to introduce the main topic of my mini lectures, which is the reflection equation, and give some background. Then I think the second lecture is the same time again, but on Thursday, where I want to do a kind of a Blackboard style lecture. So this is slides, and the last one will be slides as well, but on Thursday I'll have a Blackboard style lecture developing some algebraic and representation theory tools that we use in the last lecture, which will be kind of the research talk. And I hope that I will gradually kind of build up towards the research talk, so it's everybody can follow, and everybody kind of is on the same page that way. Please ask questions, as Robert already said. Please ask questions anytime during the lectures. I'll try to keep an eye on the chat as well, in case there's a question by chat. But if not, I'm sure somebody will. If I miss it, I'm sure somebody will point it out to me, or speak up, or send an email afterwards. That's also possible. And then even if there's an email afterwards, I can always try to incorporate some further information on my lecture on Thursday if there's any questions about today that were unanswered. So my email address is, my top two email addresses are there. You can use either. Okay, so today I want to have kind of talk in two halves. So first I want to give some overview of quantum integrability. Since it's the first lecture of the week, I thought I should address this as much as I can. So hopefully that will be kind of a gentle introduction to people who are fairly new in the field. And then in the second half, I want to talk specifically about the reflection equation, which I will call spectral reflection equation. So quantum integrability, I want to start with some kind of axiomatic setup. So there's some text here, but there will be pictures very soon as well to guide us. And basically, what I'm starting with in all this setup is a class of vector spaces. So I'm thinking about kind of a universal picture where I don't just look at one particular model, but look at the class of models. And so I want to allow all vector spaces that make sense. So I think of them as quantum state spaces for individual particles, let's say, and I want to be able to tensor them together to get multi-particle states. So I want to assume that this class C is closed on the tensor products, and the vector spaces are assumed to be finite dimensional and work over complex numbers. And so the second ingredient to this is for every pair of vector spaces in this class, a parameter-dependent linear operator, which I will call R check, and I will label it by the vector spaces V and W, and they somehow encode two particle interactions. And so these are linear maps from V tensor W to the opposite tensor product. So they somehow indicate when two particles, whatever the particles may mean in the model, are swapping. And I'm going to assume that these operators satisfy braid relations, which I will specify in a second. The nature of the parameters denoted Y and Z here, I leave in the open for now. I don't want to fix myself too much, but you can, for concreteness, you can either think that they are complex numbers as well, or perhaps formal parameters.
So when you turn your head to the right, your mic is not effective. I don't know.
I shall try not to do that. So it's a new mic. I have to get used to it, I guess. Let me know if I make the same mistake again. And so the goal of this is to develop formalisms for, or rather explicit formulas for linear operators on a big tensor product, which I identify with an n particle state space where n is some positive integer. And so I want to be able to choose any n vector spaces from my class C, and that should be well, that is a tensor product, and I should have some general formula for particular interesting linear operators on this tensor product. Okay, and so it's good to use diagrammatic representation. The formulas will become quite involved, and so the pictures will be shorthand notations at the very least for the formulas, but they're interesting in their own right. as hopefully will become clear. And so you start with the identity map. So I want to encode linear operators by pictures. And so the identity map is a good starting point. And so the identity map for V2V will just be a downward arrow. I will indicate this parameter Z as well, which is getting a free right here. There's nothing happening to it. So the identity is just the identity. And then this special operator R check will be indicated by this crossing. And I've indicated a particular convention for the right leg going over the left leg here when they're swapping. And so when I'm combining linear operators into bigger operators, you can compose them as you can compose linear operators, and that will correspond to vertical concatenation. So I'm putting them together vertically, and the arrow indicates the direction of composition. And you can also take tensor products, and that's horizontal concatenation. So I'm putting them next to each other in my pictures. So I'll give you an example of this in the next slide. And so this is the rate relation that I want to impose. And so the pictures are quite clear in some sense that they are topological identities. So these pictures are the same up to isotopies. And so you can think of this by, let's say, take the middle strand and moving it through the crossing to get this other picture. You can think of stare at it for like 5 or 10 seconds and see this is basically a picture of the Yang-Baxter equation. And so just to highlight this concatenation stuff, if you look at the red section here, this corresponds to this factor in this left-hand side of the equation. And I've put the identity map here, which corresponds to the identity map here. And then here you have this R check, which corresponds to R check. And there's a tensor symbol in between them, as I said, what horizontal concatenation should be. And the same is true for green and blue. And then I compose them in this order, red, green, blue, and it corresponds to from top to bottom, red, green, blue. And so that's precisely how we read these pictures and turn them into linear operators. And maybe it's important to stress that when you apply a linear operator to, let's say, a vector, you apply the right thrust. Right? This is how we write the composition of functions, which is perhaps slightly unnatural, but this is just the convention that is standard. So first red, then green, then blue in this case. For the right-hand side, it's kind of the opposite ordering. There's no colors there. I will try to keep the colors to a minimum, but just here, I think it was good to highlight this principle. And so this R check has a nice picture to it, but the drawback is that for non-isomorphic vector spaces, it's not an endomorphism. And so it's useful to factor out the bit that flips the vector spaces, and then you're left with the actual endomorphism of V tensor W. And so we call this R, this endomorphism. And so this is the formula that relates R check and R. And P is just a straightforward, naive flip of vector spaces, just swapping elements-wise, swapping component-wise each pure tensor. And then I can restate this R check condition in terms of this conditional R, which is the parameter-dependent Yang-Baxter equation, which is just now an equation for endomorphisms, so for linear maps that of U tensor V tensor W. So the domain and the codomain of these linear maps is both U tensor V tensor W. And so that's the Yang-Baxter equation, well known. And so this is a parameter-dependent version. And rather than saying parameter-dependent, which is useful if you want to separate it from, let's say, a universal Yang-Baxter equation, which doesn't depend on these parameters, it's more convenient, I think, to say spectral. So we call these parameters usually spectral parameters. So the benefit is it's shorter, and it's also there's other parameters in play. And so the R matrix depends usually on a parameter Q, for instance. And so I want to advocate this kind of shorter abbreviation for involving the adjective spectral. So I will use that throughout these lectures. But it just means the Yang-Baxter equation, to be precise, the parameter-dependent Yang-Baxter equation. Okay. And then some simplifying assumptions that you might want to make to have kind of more straightforward formulas. The pictures don't really simplify, but the formulas simplify. And I will do that certainly for parts 2 and 3 of my lectures this week. So one assumption you can make is that the dependence on these two parameters is actually on, let's say, the quotient or perhaps the difference of them of those two. So you can think of R check and R as well as a function, a matrix valued function of one variable, and then you can talk a bit more easily about things like meromorphic functions or rational functions, because there's a single variable at play. Anyway, and the most well-known solutions of these equations have this property, although there's also interesting solutions that don't have this property, but I will basically talk about the construction for those with this property. Another typical assumption you might want to impose is this assumption here, which is called unitarity. And this basically means that if I draw the picture I just drew for our check, and I swap the undercrossing for an overcrossing, I get the same picture. And so if that's the case, I might as well draw a simplified picture, which is no longer topological in nature, but more like just kind of a schematic drawing of an interaction. And this is what's typically done for these pictures. I find the topological picture a little bit easier in some sense to identify precisely the relation. So I want to again advocate that as well. But you can draw let's say these composite operators also with these simplified pictures. And another simplification you can do is use all the vector spaces the same. That's another typical something. Maybe you are interested first of all in a tensor product of identical particles somehow. Okay, anyway, so let's look at an example before we develop the theory further. And so I can fix another parameter Q, which will be my quantum deformation parameter. And I can just look at a two-dimensional vector space. I choose a basis, V1, V2, and then automatically I have a natural canonical basis for the tensor product, which is a four-dimensional vector space. And I can write down a possible solution to this Yang-Baxter equation. And this is a well-known solution. So Z is still this spectral parameter that appears in the equation, and Q is this extra parameter. And this is the well-known 6-vertex R matrix or XXZ R matrix. And so this is an example of a trigonometric R matrix. So in the left-hand formula with the Q and the Z, it might not be so clear, but you can parameterize it in terms of, let's say, U and eta, and then you can write it like this with hyperbolic signs. You can change it slightly in the signs, and then that's why it's called trigonometric. So I will actually work with this left-hand side notation where you have multiplicative parameters Z in the Yang-Baxter equation for convenience, but really I will still call them trigonometric R matrices because of this representation, let's say. Okay. So just to summarize what we've got so far, we have this class of vector spaces. We have these linear operators. Now I'll just use R for the time being, yet satisfying these Yang-Baxter equations. And I want to construct, let's say, commuting quantum Hamiltonians on a tensor product. And so the approach in principle is that I can use R matrix to build generating functions for these Hamiltonians. And these generating functions themselves will take values also in the linear operators on this tensor product. Okay, and somehow I need to cook up the Hamiltonians. And basically, you look at expansion coefficients with respect to this parameter Z. So the first thing you can do is you're going to assume spatial periodicity. So I'm working with periodic boundary conditions in space. And that means you can draw these pictures that I've already drawn on the previous slides on a cylindrical shell, or in other words, on a thickened cylinder. And so I still allow the braids to go behind each other, but I'm also allowing them to go around the cylinder where they don't, that's also going behind each other, I guess, but then there's kind of a bigger distance between them. So that's a way for a particle, let's say, to escape the other particles and join them on the other side without interacting with them. And so you have periodic boundary conditions. So the particles, you could say, live on a circle. And so one example of an operator on this periodic system is cyclic permutation. So I can send one particle off to the other side like this. That goes around the back of the cylinder, and the other particles just move up a little bit in space. And that's we've already seen this operator essentially. It's just one of these P operators. Okay, and then for these particular vector spaces. So U1 is just for this particle, and this tensor product, it doesn't do anything. It stays in its order, but the U1 vector space appears on the right-hand side. And you can factorize such an operator in terms of these simple P's with just non-tensor product vector spaces in their index using this formula. So you can kind of break it up into small pieces if you like. But these small pieces are not necessarily corresponding to nice pictures on the whole tensor product. And so it's this complete cyclic permutation which actually can be given this pictorial representation. And then there's actually two general approaches to quantum integrability that I want to highlight here. The first one, I think, goes back to Yang and the paper on the quantum delta Bose gas, and this is known as scattering matrices. And it's simply combining are checks, these pictures where particles swap, let's say, into a particular order like this. So the ith particle moves in front of the lower number of particles, goes around back, and it moves behind the higher number of particles. And that's an operator you can define. And then the nice thing is that if you assume the spectral Yang-Baxter equation, then these operators commute. So for different values of I, they commute. So you have n of these operators, and they form a commuting set. And so just to make it clear, I've put this p here, as we saw in the last slide as well, which is the bit of the particle that goes around the back. And here you have the VI space swapping with the tensor of all the other v's. So I've deleted the I here from the tensor product using this hat notation. What I also have done for simplicity, I will do that in the next slide as well. I'm not tensoring. I'm not writing the tensor products like I did. It should be kind of clear from the notation which vector spaces are actually involved in these R checks, and the others are well, the other vector spaces have nothing.
But sometimes.
Yes. It becomes too. Was there a question?
Yeah, no, sorry, we have a small problem with the Apple TV, but it's on our end.
Okay,
so
I can wait for a bit until it's resolved.
No, it's not a big issue. You can continue, but I'm gonna.
So that's one approach that you can have, and then the other one is perhaps better studied or better known, I guess. I think transfer matrices go back to this paper from Kramers and Vannier. This is basically what I could find based on, let's say, Baxter's book. He cites them as the original developers of this method, perhaps in a slightly different setting for the easing model, I think. But many other researchers have used this method to connect to quantum Hamiltonians. And so the idea here is to introduce an auxiliary vector space W, let's say also from the class C, and an extra parameter as well. So you have, again, the same parameters as we had in the previous picture for each of the vertical vector spaces. And then there's extra parameter Z that's associated to this auxiliary space W, which simply in the picture goes around like this. And so you can build up this way, for instance, partition functions for lattice models using stacked transfer matrices. And so this is then the formula this is then the expression in let's say, in formula form in terms of R check and R. The expression with R is a bit simpler because it has absorbed this P that corresponds to the particle going around the back. And of course, the thing that's here is an endomorphism on W tensor V1 tensor, etc. tensor Vn. And so I want to trace out W to get an operator on the right space. And so I've applied a partial trace here with respect to W. And then you have a similar statement. If you assume that the R satisfy the spectral Yang-Baxter equation, then transfer matrices commute for different values of this additional parameter. And then some further comments on this. So there's a relation between the scattering and the transfer matrices. For instance, if the auxiliary space is equal to one of the vertical spaces, and you have this condition on R, which is a fairly common condition. It's not a very stringent condition. And so this works for any I you care to choose. And then basically, if you set this extra parameter Z equal to one of the xi's, so you have an interpolant of the transfer matrix, then you get something that's proportional to this scattering matrix. And so you can actually play around with the pictures and get a very straightforward proof of that. So perhaps an exercise for any students that haven't seen this yet, this nice fact. It's a really nice exercise. If it helps, you can assume all of the V's and W are isomorphic. And so again, with the same assumption, but now for all I, the quantum Hamiltonian can be obtained by a logarithmic derivative of either the transfer matrix or the scattering matrix, provided after you've taken this logarithmic derivative, you set all these parameters equal to 1. And so this corresponds roughly to taking a particular coefficient of one of these generating functions, T or S, and pinpointing, saying that is my Hamiltonian, and you can actually connect this with particular known expressions for quantum Hamiltonians. Higher derivatives, let's say, correspond to higher order Hamiltonians. The transfer matrices can be diagonalized, at least in certain cases, via what is known as the algebraic beta ansatz, which was developed by the St. Petersburg School in the late 70s, early 80s. This is a well-known solution method. I'm not going to go into detail here, but that's something to be aware of. And also the scattering matrices, which I've kind of glossed over a little bit, but they are also have a rich connection, like a strong connection with a rich area of mathematics known as QKZ equations, quantum KZ equations. In this special case where the R matrix has a dependence on the quotient. And so these scattering matrices are simply special cases of the operators appearing in these quantum KZ equations, which are difference equations, or rather multiplicative difference equations. I've also mentioned here for the, let's say for any students that they're starting in the area, some kind of well-known textbooks and surveys on this material. Okay, but hopefully that serves as a motivation for the study of, let's say, R matrices. And so the question is, how do you construct them? If you've got a good construction methods for R matrices, you have access to a large class of integrable models. And so are there algebras actually that contain solutions of this Yang-Baxter equation with interesting finite dimensional representations? So in that case, you can just set C equal to the class of representations of modules of this algebra. And then you get many R matrices by just looking at the image of this R matrix that's inside the algebra. And so quasi-triangular Hopf algebras are good candidates for such algebras because they have this this special internal R matrix, let's say, built in. And so one thing you can do is as follows. You can look at the loop algebra of a finite dimensional semi-simple Lie algebra over the complex numbers, let's say SLN for simplicity. And so the loop algebra already has this kind of parameter dependence in terms of this desired parameter built in somehow. You can quantize this loop algebra. You get what's known as the quantum loop algebra, and that can serve as such an algebra A. So I will give more details in the next two lectures on how this quantum loop algebra is defined. It's closely related to an affine to the affine quantum group, which is a special type of quantized Kac-Moody algebra and has a rich representation theory associated to it. Has been studied since the 80s as well by many authors. And so these are Hopf algebras. They are not quite quasi-triangular, but they are close enough so that the whole machinery still works. And so that's what we call up to completion. And on Thursday, I will explain that in more detail, how to say this properly, how to set this up properly. And it's kind of correct to say that for such quantum loop algebras, the universal approach that I kind of outline here works and produces, for instance, this 6 vertex R matrix that we saw already, but many more, let's say, bigger siblings of this matrix. So many more trigonometric solutions of the Yang-Baxter equation. And this goes back to work from Jimbo and Drinfeld in the 80s. And maybe one more comment here is that you can recover the quantum group from such an R matrix, even like an actual matrix. I don't mean the universal R matrix that's inside the algebra, but let's say the image of it in a particular suitable representation via the RTT presentation of the quantum group. So there's a kind of a two-way street. I will actually focus more in these lectures on the first direction, where I start from an algebra and get the linear operators on the vector spaces. Okay, so that's really what I wanted to say about kind of general quantum integrability. So if there's any questions, please stop me at any time. And if people are fairly happy with this, we can move on to the reflection equation, which is kind of an additional, let's say an additional element to this idea of quantum integrability when we have boundaries involved. So boundaries destroy symmetries, but if you choose the boundaries carefully, they won't destroy all symmetries. You're still left with some symmetries, and you'll still have some kind of integrable system, and that can be made quite precise in terms of other or related formalisms in terms of scattering or transfer matrices. And so we need some new ingredients, however, to write them down properly. So the given datum in terms of this class C of vector spaces and these R checks or these Rs, these matrices, what I can do in terms of the pictures is I can introduce a puncture. So I'm introducing an obstacle, if you like, for the braids to deal with. They have to perhaps go around this obstacle, and that corresponds to a new building block, a new generator of, if you like, of a braid group or something like a braid group, and that's what we call K. And this is also an endomorphism of V, so it's also a matrix. So we call it the K-matrix. And the assumption that's extremely useful, and I think on Thursday I'll have some time as well to explain why this is the right thing, is to assume that this parameter that is associated to all these lines gets inverted. So perhaps you have to assume it's a non-zero parameter if it was a complex number, but in any case, this is a very, very cool assumption that really is very powerful and just gives the right type of results. And I'll explain a bit more in detail why that kind of underlying mathematics of it, why that's the case. Again, you can make this kind of simplifying assumption. Again, this is a form of unitarity, it's also known as, let's say, boundary unitarity. Again, this means that the corresponding picture with the lines interchanged, where this one goes under this puncture and then over this puncture, correspond to the same thing, the same linear operator. If that's the case, you need to bother with under and over crossings, and you can write a simplified picture. And well, you can see the picture, it just looks so much like a K. So this was a very clever notation. This is due to Sklyanin, although certainly probably his least contribution to the field, but it's a very useful notation in that sense. Okay, so it looks like a K and we write it like K. And then the equation that you need to impose, the natural equation that you need to impose on such an element, well, it needs to be governed by some topological identity. And the topological identity involves two strands and this puncture. And so if two strands wrap around the puncture, wrap around this obstacle, then there's two ways for that to go. And if you write them like the left and the right hand side of these pictures, and you stare at this for maybe 20 seconds, you can see that these are actually topologically the same picture. So perhaps what I find the easiest thing to do is to look at this this part, kind of pull it to the left to make the loop around the puncture bigger, and then pull it up and then let it shrink down again. And then it has swapped place with the other. Perhaps that's the easiest way to look at it, but there might be different preferences. But for me, that works. And so these are natural equations from a topological point of view. And so let's impose them on our datum consisting of R and K. And so in terms of R checking K, it looks like this equation. I've written it here. And in terms of R and K, this is the same equation. I've just taken care of this factor P. Okay? And so this is a promising equation in terms of that's the kind of same topological thing as the Yang-Baxter equation. It's a similar type of equation. So perhaps we can combine them somehow, these ingredients, and construct more composite operators. And so I won't give you the precise formulas for the corresponding scattering and transformations. I'll just give you the pictures, and then perhaps it's a nice exercise to recover the formulas. Although I'll cheat a little bit, because so far on the last slide there was only one boundary, and so you have to pinpoint. Well, it's very convenient to have a second boundary, so that the particles live on a compact space. In this case, an interval. Of course, the previous case, it was a circle, which is also a compact space. And so there's two boundaries, and then you can form this kind of scattering matrix like this, which was actually introduced by Cherednik as part of a QKZ story. So he wrote like a QKZ equation for, let's say, two boundary systems. And so it's in principle is the same, that you go in front of. So again, this particular I that you choose, particle I, goes in front of certain particles and goes behind, goes around this obstacle, goes behind the particles, and goes around this obstacle, and now goes behind these. Again, if you impose the suitable reflection equations, because you have to say something about this one, this K-matrix, and suitable Yang-Baxter equations, you get commutativity. You have the transfer matrix, which predated this scattering matrix. It was due to Sklyanin in 88, and it's the same story. You have to choose a particular solution of another type of reflection equation for the other boundary, and then you can deduce that the two transfer matrices commute for different values. values of the Z. Okay, then there's again a connection between these two pictures. So I hope it's not bad if I cite my own work here, because I was quite happy to write this down precisely a few years ago. Again, relying on certain basic assumptions on the R matrix datum, such as this R at 1 is P, things like this, and you can make this connection precise. It's in the end, then it turns out to be the same connection as for the periodic system. It's a bit more difficult to prove it. Okay, and so maybe one more comment here on these pictures, that this K matrix here is not quite the same thing as this, and that's why the relation between these two formalisms is not quite straightforward. But again, for suitable R matrices, there's natural isomorphisms between solution spaces of these reflection equations for the right, the two different reflection equations for the right-hand side. Maybe especially considering what I'm going to say on Friday and on Thursday as well, there's a basic formalism in terms of bi-algebras that was observed by Kulish and Sklyanin in the early 90s, that certain co-ideal subalgebras of this kind of master algebra A, this algebra that somehow contains the bulk symmetries, correspond to boundary symmetries, and then it is very pleasant to assume it is actually a co-ideal subalgebra. More generally, it could be a co-modular algebra over this A, and I will explain in Thursday a bit more in detail how that works. But they identified this nice kind of bi-algebraic assumption and developed the theory further in that direction, and that was the basis for much later developments from the last, let's say, 20, maybe 10 years in universal solutions for the reflection equation. It really is grounded on this observation. I should give some examples, I think. So I want to recall this 6 vertex or XXZ R matrix that we already saw earlier. So again, I'll just stick with this notation in terms of Z, not the actual trigonometric formula, but we will call this the trigonometric R matrix, and the K matrices below we'll call them trigonometric K matrices nevertheless. And then it's quite easy, just with some pen and paper and maybe a rainy Sunday afternoon, to give a classification of the solutions of the reflection equation with this R matrix as a given. So in this case, I assume that the two vector spaces are V, they're the same for simplicity. And then you can find a classification, and it corresponds in a kind of a nice selection of, let's say, matrices that become easier as you move to the right. So you have this most general equation. I think this was found in the 90s at some point. And you have this kind of intermediate triangular form. You have a diagonal version. This was known to Cherednik and Sklyanin in the 80s, and Sklyanin used this to this matrix to explain his boundary version, two-boundary version of the algebraic beta ansatz. But it still has a free parameter psi in it, which is nice for let's say physical interpretation. You can kind of somehow think you can tune the boundary interaction that way, and you can go all the way down to identity. So there's some free parameters floating about here, also going down in number as you go to the right. And this is a classification up to scalar multiples, of course, because you can multiply in this reflection equation everything by scalars, and also some basic transformations that in some collaborations with Rygalski's in a slightly different setting we call dressing and rotation, which is not super important here, but basically dressing means you can introduce further free parameters in the off-diagonal entries. So it's relevant for the first two matrices, and rotation roughly means kind of rotating, roughly speaking, the matrix by 180 degrees and doing something with the powers of Z, and that gives you another solution as well. And so I didn't write those down, but they're roughly the same as what you can see. Okay. Of course, the question could be, well, how can we construct solutions in general of this equation without actually having to solve this? You can imagine that solving the reflection equation for a given R matrix might be a lot of work. So you can manage to do it probably for this example, and maybe for some, like maybe slightly more complicated R matrices. But at some point, you want to have some more advanced method for this. I'm just having a quick look at the slides. I think I've got about 15 or 20 minutes remaining. So that's quite good. So let me give you one more interesting generalization of the reflection equation. which is kind of natural from the topological perspective. And I'll show some kind of fancy pictures here, and I'll tell you on the next slide why we should care. So this, at the moment, it's just an exercise in kind of more kind of braid group stuff. So I can assume that instead of strands, that the particles don't correspond to strands, but to ribbons, two-sided ribbons. And so for to distinguish between the two sides, I've colored them white and red. And so I may assume, for instance, that the K-matrix is not just a strand going around this obstacle, but it swaps sides. So it's kind of, it hugs the obstacle and then comes around with the other side showing. That's kind of a fairly natural picture. At least I thought it was a fairly natural way of encoding such a generalization. And then if you have that, you of course have to have two particle interactions of different colors, let's say, or mixed colors. And so it's actually sufficient to look at 3 instead of the 4 that you might expect. And so you could have just 2 showing, let's say, the front side, 1 showing the back, 1 showing the front, and 2 showing the back. And so I indicate that in the notation with pluses and minuses. So plus stands for white or the front, and minus stands for red or the back. And then the natural condition to impose on this K is this condition. Again, it's a topological condition. You can stare at it for a bit and you can see it's true. These pictures are the same up to isotopics. And so in terms of the formulas, I've written down the equation here. And so you can see here that you have a mixed, let's say, mixed white-red R matrix. And here you have only red strands or ribbons. And here you start with just the white side of the ribbons, and here you have a mixed one again. And so you never get the one with white going here and red going here. And that turns out to be very useful because we will be able to produce solutions of this. But in the quantum group formalism, the mirror image of this, let's say, doesn't exist. So you only have these 3 for this formalism, and you can only create these 3 from the quantum group construction, from the universal construction. Then these R matrices, of course, have to satisfy various Yang-Baxter type equations that I didn't draw, but you can imagine there's different combinations for different colors. So there's actually 4 particular equations you could naturally impose. So why do we care? So I've been giving you a 1-boundary formalism with ribbons. It extends to a 2-boundary scattering matrix or even QKZ equation formalism. That's actually due to Cherednik, although he didn't draw these ribbon pictures, but it's the same equations that are going on there in this paper from the early 90s. He told me at some point that he was very happy with this generalization, but he couldn't find new examples. So he just had said, well, it's a generalization of existing things. It's a unifying framework in some sense, which is quite nice. But anyway, the universal formalism that I will explain on Friday for these K-matrices sometimes produces, let's say, solutions that are actually require this ribbon formalism. You can also write down a transfer matrix formalism for these ribbon particles, which is work in progress. But it's, from a topological perspective, it's kind of clear how you have to draw the pictures, and then you kind of work backwards and write down equations for this. I mean, for the other one, and compatible here, I write compatible, meaning again that you can relate the scattering and the transfer matrix picture. And so, as Cherednik told me, you can specialize to existing formalisms as follows, and this is actually quite nice. So you can simply just replace all these kind of colored R matrices by just the same thing. Let's say they're all the same. So the ribbons have the same size, so you might as well take it from the strands. Then you get the picture, the formalism that we already discussed, just a normal 2-boundary formalism from the 80s, let's say. And so this somehow corresponds to particle-particle scattering at the boundary. So the particle interacts with the boundary and stays a particle. It doesn't go into its dual representation. But at the same time, people developed a formalism where the particle becomes an antiparticle after interaction with the boundary. So somehow that requires a different reflection equation. But this is also incorporated in this generalized version. You simply, this mixed R matrix has to be kind of the partial transpose inverse of the other R matrix. And then you get that formalism automatically for free. And the really nice thing, I think, is if you set the mixed R matrix equal to the identity, and the other two just the same, you get a periodic formalism, provided you also choose the matrix, the K-matrices to be trivial. And so somehow, rather than you have periodic systems and you have boundary systems, which are kind of completely separate, with separate theories and separate frameworks, you can somehow combine them together if you permit this generalization with ribbons. And so, as I already said, I kind of need to motivate it like this because the universal approach sometimes doesn't give a solution of the original reflection equation of the 80s, and you need this more general version with ribbons. There's actually a still more general version for which I can't draw pictures. Maybe a very clever person could draw pictures for a more general version, which is due to Friedel and Meyer, 91, with basically 4 different R matrices rather than just 3 different R matrices. Okay, so this is basically the last slide. I just want to kind of formulate some questions that I want to study further in the next 2 lectures and outline my kind of plan for the next 2 lectures. So I already hinted at this. Is there a boundary version of the universal approach that gives us trigonometric R matrices from quantum loop algebras? So this is the approach Jimbo and Drinfeld developed in the second half of the 80s with slightly different perspectives, and so we can kind of follow both perspectives to some degree quite closely, it turns out. The second question is some kind of classification question. Can you actually get all trigonometric images? So I gave you a little classification for the simplest case, and you don't actually get all of them, but we have a good idea of how to, or what kind of things are necessary, let's say, to extend this picture, and somehow the basic axiomatic framework that produces these universal solutions of the reflection equation seems quite general, and this hopefully permits for a description of all trigonometric K-matrices that we have, and maybe that helps with the classification. And you could also think, well, these are kind of in some sense basic questions because I'm just talking about solutions of this reflection equation. What if I look at these composite operators, transfer matrices or QKZ equations? Are there boundary analogs of results for these more composite operators that are well known for R matrices, but perhaps unknown for K matrices? So perhaps some open questions that we can discuss. And so the plan is that on Thursday, I will kind of give a Blackboard style talk where I will do a bit of algebra and representation theory and a hint of category theory as well, just for good measure, just to present, just to set ourselves up for the last lecture. And then in the last lecture on Friday, we will give a confirmative answer to question 1. I will sketch what we know for question 2, or at least what I know about question 2. And we'll discuss some possible, well, open questions for more kind of a more advanced nature, let's say, where you have these composite operators. So that's what I had for today. So I hope that was useful. But any questions, please let me know.
Thanks very much, Bart. Are there any questions?
I am surprised by your way to represent the K-matrix, because I would have thought that it had more to do with some particle that reflects around the wall. But here you seem to say that it's a particle that turns around some bar.
Let me go back to the pictures that where I introduced this idea. And so indeed, so for instance, if you talk about quantum loop algebras and you talk about finite-dimensional representations, if these are irreducible, then you can actually prove that the R matrix has this unitarity property, and a similar thing turns out true for the K matrix. So in fact, without loss of generality, for most interesting representations, you can work with this, let's say, simplified picture or the standard picture that we know from, let's say, vertex models. In order to have a topological underpinning for this, you have to have some kind of obstacle here. There's no other way to write down topological identities of a topological nature. And so a thing you can perhaps that might make it kind of more acceptable is you can also think as the boundary being itself a particle and carrying a representation of some quantum algebra. And then you have then you would expect just like the R matrix is some kind of topological interaction between two particles, at least in the diagrammatics, the K-matrix is of a similar nature. And it just, in a way, is two R checks on top of each other. And because the particles bounce off each other, they should be ordered in the same way before and after. So you need two R checks. And so that kind of motivates perhaps this kind of slightly unusual picture, perhaps. If I may add one more thing to that, actually, the equations, the reflection equation itself, if you take away all the spectral parameters and just look at the braid relation, it's precisely what is known in the literature on braid groups as the cylindrical braid relation, or type B braid relation. And it is precisely what you get when you have a number of points in a punctured disk, and you trace what happens with these points as they move around this puncture, which is very close to the picture I've sketched here. So this is a well-known correspondence when you don't have the spectral dependence.
Hi, so my question is maybe related to the point 3 that you raised at the very end. So,
yeah.
But is there a natural generalization of your formalism to the case of elliptic models instead of trigonometric ones? Or I guess it's a hard thing.
This is a hard problem, and so my formalism is really not. It's really an answer to question 1 only at the moment. But that formalism, at least in principle, is fairly general. And so it's very well possible that you could use the same formalism, at least, let's say, for rational K-matrices, or for K-matrices associated to Yangians. Now, I think elliptic quantum groups properly defined aren't quite quasi-triangular Hopf algebras, even up to completion. And so you would need to tweak some more to get that working. But it's still of a fairly general nature that I think it is the right approach that needs to be developed further. But that's a very good question, and I wish I knew the answer.
I had a question about your generalization.
Yes.
Plus minus generalization. I mean,
Yeah.
Is it possible just to incorporate this within the standard picture just by extending the representation to include these extra indices? So, for example, in SLN, you could have, or SL3, you could have 3 going to 3 bar, and that would be a plus, a K going to from plus to minus. So
I would say that's an example of such a K-matrix, but it's not restricted to this particular behavior. So this is kind of the most general formalism you could come up with that is compatible with the braid group interpretation. And so you can get something like this, but I think it is more general with that. And so but the fact that you can also get the periodic transfer matrix and scattering matrices from this suggests that it's more general than that.
And can you add more, instead of plus minus, can you have 0, 1, 2?
Oh, I see. Okay. Somehow, so the idea behind this, when I read Cherednik's paper that we came up with this, is that you use the other boundary to go back from minus to plus. So the only way that the particle changes from plus to minus is by interacting with boundaries. And so it's natural then to have 2 states, or not two states, that's not the right word, but two types of vector space structures. And so perhaps you can generalize it further, but I don't really see the precise braid group picture or the application to integrability, but it's one can try.
Hello, Bart. Have you some example of this type of matrix, which is not trivial in the sense they are different? You have R plus plus, different of R plus minus, and so on.
Yes. So I can kind of look ahead to what I will say on Friday, and basically you can think of R. So let's forget about the checks. Let's talk about R. R plus plus would just be the image of the universal R matrix, suitably interpreted, of a quantum loop algebra. And then R minus plus could be a twisted one, in the sense that before I apply the representation map, I apply particular algebra automorphism in one leg of the universal R matrix. And that would be an example of such a R minus plus, which is different. And then R minus minus would be with the algebra automorphism applied to both legs. If the algebra automorphism is not a Hopf algebra automorphism, R minus minus will be different than R plus plus. So even those kind of things which are most alike in these pictures, because they have the same color, can be different because they have this this psi, let's say this algebra would more apply to both legs of the R matrix. And it might not be that it simplifies to the R matrix itself, the universal R matrix. So that's the kind of things that I naturally get from this universal formalism that tells me we get something really new here.
It is not connected to the point 2 of the other slide with the transpose.
That can be, that's an example. So let's say that in some cases this psi can be chosen so it disappears in the end. And R minus minus will be R plus plus. And then indeed for this intermediate one with the mixed colors, it can be that you get this partial transpose. And that is usually the remnant of a diagram orthomorphism. So let's say affine SL2 has a diagram orthomorphism that swaps it to Dinkin nodes. That can be on one leg of the universal R matrix, and it will change. It will not be the same R matrix. If you apply to both legs, it will be the same R matrix because it's a whole algebra orthomorphism. So that gives rise to these partial transposes. So that's actually already known. That's not something we found. It's already known in finite type R matrices, R and K matrices. How this partially transposed reflection equation arises is in the, let's say, the constant version, the parameter independent version. That's quite well known.
Any other questions? Well, let's, I guess we thank people at the end, despite the fact that it's a school, so let's thank Bart.